Okay, so as promised, I'm going to give you a more detailed explanation now of the number of signals. So we talked about the number of signals in this spectrum here, and we said, all right, so we're going to call this, where am I here? We're going to call this one signal here, another signal here, and another signal here. And we said that these are going to represent three different kinds of hydrogens, right? The number of signals is equal to 3, which means 3 kinds of hydrogens. Okay? So, and we gave the example that this is the spectrum for ethylbenzene, where this is that kind of hydrogen, right? This is a methyl group, right? Here's a methylene group, that's CH2, and these are here. And you wouldn't know this unless someone told you, right? I haven't given you enough information to know this yet, but these, can you see how this has a different environment than this one? These guys are right next to a benzene ring, and these guys are right next to a methylene, but not next to a benzene ring, so they have a different electronic environment. And the hydrogens that are along here have a different electronic environment yet, okay? And these 5 are here. All right, so that's what we mean by different kinds of environments. Now let's get a little more detailed, all right? Because we have a very sophisticated apparatus, the nuclear magnetic resonance apparatus, which will give us super precise measurements. So let's get a little more precise than that. The number of signals in a proton NMR spectrum indicates the number of different kinds of protons, which we said previously. Now we're going to call those protons we're going to call them equivalent or chemically equivalent protons, all right, chemically equivalent protons. And so I said in the previous slide that these protons, the hydrogens there, are not equivalent to those 3, right? So, but if they're chemically equivalent, then that means that they fall in the same signal. They're going to be either homotopic or enantiotopic, all right? And so we're going to take a few slides to talk about what is homotopic and what is enantiotopic, all right? We're going to split this pretty thin. So homotopic protons are protons that if you flip them, you can't tell the difference, right? So here's 2 different hydrogens, and if you switch those, you're going to have exactly the same compound. So these 2 then are homotopic, all right? These 2 are different hydrogens, right? But if you switch them, you can't tell the difference. And I would say the same for these 2, all right? So another way to do that is to suppose that you had a replacement. So suppose you took this hydrogen and you made it a deuterium instead, all right? So if you made this a deuterium, would it be the same if you flipped it over? And yes, these 2 are the same compound. So this is a very robust test for it. It's going to require a pencil, I think. I don't think you're going to be doing this in your head very easily. So if the resulting compounds are identical, then the protons are said to be homotopic. I'm getting a text here. I don't think that's anything important for me. Okay, I'm going to move on. I'm sorry, pardon me for that. I've got several things I'm trying to take care of here. So if the resulting compounds, all right, so that's homotopic, okay? Now, enantiotopic are going to be, it'd be like enantiomers. We get the same thing. We get the same thing for enantiomer. So if a molecule has a plane of reflection that makes one proton mirror the image of the other, then it's enantiotopic, which means it's going to have the same electronic environment. So both of these hydrogens have the same electronic environment because you have some kind of a plane that goes between actually that includes the fluorine and the chlorine, and you can see it's reflectionally reflexive. Okay, so those are enantiotopic, and it would be like enantiomers. So if you took circle and square, that would be an enantiomer for square and circle, right? Those would be enantiomers if we had. We use those terms before. So those are enantiotopic protons, and they are also considered chemically equivalent. That means that their electronic environment is the same. Okay, the replacement test is universal. It's going to work all over. We just did this a minute ago, and we do it again for this one, and you see that these are enantiomers now. Sort of implied that with the previous slide. Okay, so now to determine if protons are equivalent, we look for rotational symmetry. In other words, can you flip it around and see if they're if you can flip it around and see that they're rotational on an axis, by the way. If you can flip it around and put it on its mirror image, then yes, it's homotopic. If you can't, but if there's a plane of symmetry, then you can call it enantiotopic, okay? And if neither is found, it is not chemically equivalent, and it's going to technically give you two different signals. So if you've got two that are not technically equivalent, chemically, if you've got two that are not chemically equivalent, H1 to H2, then they're going to technically give you two separate signals. Although I must warn you, sometimes the signals are so close to each other that they're right on top of each other. It looks like one signal. Okay? So the replacement test in the case of non-equivalent hydrogens, non-chemically equivalent hydrogens, these are not chemically equivalent, it's going to give you diastereomers, right? So if I took this one and made it a D, and then the other one made it a deuterium, C, deuterium, and deuterium, these are diastereomers with respect to each other, and they're called diastereotopic. The term is not so important in my view, but it's valuable, right? Because we've used diastereomers before. The protons are called diastereotopic, and they are not chemically equivalent, and they will give you two separate signals, okay? Again, the signals may be right on top of each other, so you don't absolutely know for sure. If the protons are neither homotopic or enantiotopic, they're not chemically equivalent, which we already said. We consider this here below. These protons cannot be interchanged by rotational symmetry or reflectional symmetry, and so these two protons are enantiotopic. If you, or I should say rather, diastereotopic. They are not chemically equivalent. And if I encourage you to stop the video here, replace one of them with a deuterium, and see, or rather, replace one of them with a chlorine. Do that, and then name the compound, and then replace the other one with the chlorine and name it, and you'll see that it is not. It is not the same thing. Okay, those hydrogens are not the same thing. So here are a couple shortcuts that you can consider to make it easier for you. Number one, the two protons on a CH group will be equivalent if there's no chirality centers in the molecule. If there are no chirality centers, this is, I think, useful. If there are no chirality centers on the molecule at all, two protons on any CH group are going to be equivalent. And also, the two protons on a methylene group will not be equivalent if there is a chirality center in the molecule somewhere, okay? So these two are equivalent because there's no chirality center, and here's a chirality center, so these two are not going to be equivalent. That's a nice shortcut. I think it's going to save you some grief. Okay, so let's do another one. The three protons on any methyl group will be equivalent to each other always. Okay, because there's rotation about the axis of the methyl group. And then multiple protons are equivalent if they can be interchanged with each other through a rotation or a mirror plane. So you can see that we can rotate that molecule and turn it around. So all four of these are chemically equivalent, and they're all going to give rise to the same signal. Okay? Recall that cyclohexane, oh, this is interesting. Recall that cyclohexane has got two different positions for protons, right? Axial and equatorial. Now, normally at room temperature, this cyclohexane's flipping back and forth. It's going from there to like that is flipping up, right? So this is going back and forth between an axial and an equatorial very fast at room temperature. However, and so at room temperature, there's only one type of proton observed in a proton NMR for cyclohexane. However, if we go really cold, if we go super cold, then the ring flipping is slowed, and we actually see two signals at that point, one for the axial and one for the equatorial. Okay, and so that's a more detailed explanation of the number of signals. Please don't lose sight of the important feature, though, and that is, generally speaking, you can look with your eyes and you can see if hydrogens are equivalent to each other, if their environments are equivalent, and you can group them into groups, and the number of groups that you have is going to be the number of signals. Number of equivalent hydrogens is going to be the number of signals.